So back in 2009, this software engineer decided that the absolute best way to solve the really complex problems of modern web servers was to to resurrect a programming philosophy from 1958.
Yeah, which sounds kind of crazy at first.
Right. I mean, it really does. But welcome to our deep dive into your CS330 notes, specifically Class 26, where we're going to figure out exactly why he did that. You've spent time unpacking all these abstract theories of functional programming.
Right, the big picture stuff.
Exactly.
Yeah.
But our mission today is to actually get our hands dirty. We are looking at the real syntax and the mechanics of Clojure.
Because, Rich Hickey, the creator of Clojure, he basically looked at imperative programming and just realized it was fundamentally broken for modern multi-threaded apps.
Yeah.
There's actually this great quote from your notes by Greg Wilson that sums it up perfectly. He says, the history of programming language is basically a chronicle of our attempts to turn Fortran into a Lisp-y that non-geniuses can use.
I love that quote. Lisp has this almost mythical reputation in computer science. Like your class slides even have that classic XKCD comic.
Oh, yeah, the one with the universe unfolding.
Yes. The programmer is reading a Lisp book and gets this divine enlightenment, sees the naked structure of the universe, and then gets handed a massive stack of parentheses. And the punchline is that they are elegant weapons for a more civilized age.
It's so accurate, honestly.
So before we even look at the syntax, I want to wrap my head around the lineage here. If Lisp is this elegant lightsaber, why did Rich Hickey even bother building Clojure? Like, why not just use Lisp for everything?
Well, pure Lisp is incredibly elegant, but, elegance doesn't pay the server bills.
Right. Good point.
Hickey knew that modern software relies on these massive ecosystems of libraries, and it has to run anywhere. So he made this really strategic architectural choice. He built Clojure to run directly on the Java virtual machine.
The JVM?
Exactly, the JVM, and also Microsoft's .NET runtime.
Which, okay, that feels like a huge contradiction to me because Java is, strictly object-oriented, it's super verbose, and it's all about mutable state. But Clojure is this fluid, functional thing. It's almost like taking this beautiful vintage sports car engine, which is Lisp, and just dropping it into the chassis of a commercial semi-truck.
That's a really good analogy, actually. The contrast is totally stark, but the synergy is why it's so brilliant. You get the mathematical purity of that functional engine, but you also get the indestructible enterprise-level Java chassis.
Okay, that makes sense.
But Hickey didn't just stop at an engine swap. He completely re-engineered how the language handles time and state. And that's why Clojure is so good at concurrent environments, like in Java or C if you have multiple threads trying to change the same variable.
It's a nightmare. You need mutexes and locks and all that.
Massive headache, exactly.
Because, in imperative programming, a variable is just a bucket in memory, right? If thread A and thread B both try to dump new data into that same bucket at the exact same millisecond, your program just crashes. Or worse, it corrupts the data.
Right, and Clojure just throws that whole mutable bucket concept in the trash.
Really? Just completely?
Totally. It uses immutable data structures. It separates state from identity. So think of an identity in Clojure not as a bucket, but like a name tag that points to a specific value at one exact point in time.
Okay.
So if you need to update it, Clojure doesn't overwrite the old data. It creates a brand new version of the data and then just moves the name tag over to the new one.
Wait, I get immutability in theory, but if I'm, say, making copies of a massive database structure every single time I change one integer, isn't that going to just destroy my computer's RAM?
Well, it would, yeah, if it was actually making full copies.
Yeah.
But he uses something called structural sharing.
Structural sharing.
Yeah. Since the underlying data can literally never be modified, the new version just shares all the unchanged memory references with the old version. Only the tiny little piece that you actually changed gets newly allocated in memory.
Oh, wow. Okay, so if neither version can be altered after the fact, they can just safely share like 99% of their underlying memory.
Exactly, without any fear of one accidentally sabotaging the other.
That is super clever.
It is. And that leads right into Clojure's built-in concurrency. To manage these changing identities, it uses STM, software transactional memory. It basically treats your RAM the way a SQL database handles transactions.
Oh, so if two threads collide,
the STM just detects it, rolls back one of the operations, and retries it safely. No deadlocks, no manual thread locking, just automatic concurrency.
Wow. Okay, so we've got this amazing, safe, functional engine running on the JVM, but having a great engine doesn't mean much if you don't know how to drive the car.
Very true.
So let's talk about the syntax shock, because coming from C or Java, popping the hood on Clojure code is, well, it's deeply disorienting for imperative programmers.
Oh, for sure. The disorientation really comes from this concept called homoiconicity.
Right, which the notes say basically just means code is data.
Exactly. In Clojure, the entire language is represented using lists. And these lists are just enclosed in parentheses, separated by whitespace, no curly braces, no semicolons. The whole program structure is literally just a nested data structure.
Yeah, the thing that really tripped me up was the prefix notation. Like in Java, if I'm doing basic math, I type the first number, then the plus sign, then the second number. But in Clojure, the operator is always the very first element inside the parentheses.
Right, so it's parentheses plus 2, 3, close parenthesis.
Exactly, which feels like Yoda speak for math. Like instead of saying, I eat food, you're saying eat I food. It's so weird.
It does take a minute to get used to. But think about what a Java compiler actually has to do. When you write standard math, the compiler has to parse your text and build an AST, an abstract syntax tree, just to figure out the order of operations.
Oh, right. The root of that tree is the operator, and the leaves are the numbers.
Exactly. So by forcing you to put the operator first, Clojure is basically making you write the abstract syntax tree directly.
Oh, I see. You're completely skipping the parsing ambiguity.
That's the secret sauce of Lisp languages. You're writing the raw structure.
Yeah.
And to practice this, Clojure uses the REPL, the read evil print loop. You just type COJ in your terminal on the lab machines, and you get this interactive sandbox. Every list you type is instantly evaluated.
Actually, the notes have a really interesting example of this. If you type out a print statement for hello world, the REPL prints the string to the console, but then it immediately spits out a second line that just says nil.
Yep, the classic nil.
Which, if you're a Java student used to void functions, seeing nil pop up like a result feels like you just broke something.
I know, it looks like an error, but it's actually Clojure enforcing its functional purity. Because in an imperative language, a void function just runs some instructions and stops. But in a functional, expression-based language, every single set of parentheses has to evaluate to a concrete return value.
So the print function works. It prints the text, but mathematically it didn't compute a new piece of data to hand back.
Exactly. Printing to a screen is just a side effect. So to satisfy the rule that everything evaluates to something, it hands back nil.
And the REPL prints nil because its whole job is to literally read, evaluate, and print whatever the final result is.
You got it.
But wait, that begs a huge question. If every single list evaluates as a function, how do you just store raw data? Like if I open parentheses and put in a list of numbers, the language is going to look at the very first number and try to execute it like a command.
Right. We would throw an error. So this is where we finally step away from parentheses. To define a variable, you use the def keyword. But to group a collection of raw data that shouldn't be executed, you use vectors.
And vectors use square brackets instead of parentheses.
Right. Square brackets.
And the notes mention something kind of wild about punctuation inside those vectors. Commas are completely optional.
Yeah, commas are literally treated the exact same as white space. You can use them if it helps your brain parse the list, but idiomatically, Clojure developers just use spaces.
That's fascinating. It really forces you to think of the data as a structural sequence, not just a string of characters bound by grammar rules.
Exactly.
So, okay, we've got immutable data, we've got vectors, but no language exists in a vacuum. If you're building real enterprise software, you need date parsers, math libraries, network sockets. How does Clojure handle that without reinventing the wheel?
That goes right back to the JVM chassis. Clojure has totally frictionless Java interop. If you need the Java math library or a new java.util date object, you just call those Java classes directly from inside your Clojure list.
Just right in the code.
Yep, you literally just put a slash between the Java class and the method name.
Okay, looking at the syntax in the notes, it is incredibly terse. But let me push back on this a bit. If my Clojure program is ultimately just calling Java math libraries and Java date objects under the hood, why am I bothering with the syntax shock? Why not just write the whole thing in Java and save myself the headache?
Because Java is just your toolbox.
Yeah.
Clojure is the advanced assembly line.
Okay, expand on that.
You use Java interop to grab the raw materials, like a network connection or a date object, but you pull them into Clojure so you can process them using functional paradigms. Paradigms that would take hundreds of lines of boilerplate code to pull off in Java.
Ah, I see.
The power isn't the tools themselves, it's what you can do with them once they're inside Clojure's ecosystem.
That makes a lot of sense. Extract the utility of Java, but manage the logic with Clojure. And that logic pipeline relies heavily on how Clojure handles functions. So let's look at function creation. In Java, a function is this static block of code permanently tied to a class. But in Clojure, functions are first-class citizens. The notes say you use the defin keyword to make a named function, but they also show just m without the def, which makes an anonymous, nameless function. Why would I ever want a function with no name?
Because anonymous functions are the absolute foundation of higher-order programming. They let you pass behavior around the exact same way you pass variables around. And more importantly, they let you write functions that generate other functions on the fly.
Okay, now we're getting into the deep end. This brings us to closures, right?
Yes, closures are a huge part of your notes.
So there's this specific function in the notes called adder, and honestly, tracing the execution path is total brain bender. It's an outer function that takes a parameter, but instead of returning a math calculation, it returns an inner anonymous function that takes a second parameter.
Right, so let's just walk through the mechanics of it. You have the outer adder function, and it takes an argument, let's just call it x. Inside its body, it uses that fn keyword to spin up a brand new anonymous function that takes an argument y. And this inner function adds x and y together. So when you call the outer function with a number, it doesn't do any math. It just hands you back that newly minted inner function.
Oh, so it's essentially a factory that builds custom calculators.
Exactly.
The outer function is the factory.
Yeah.
So if I pass the number -500 to the factory, it manufactures a new anonymous calculator whose internal x value is permanently hard-coded to -500.
Right.
It hasn't done any actual adding yet. It's just sitting there waiting for me to hit a button with the y value.
That is the perfect way to visualize it. And that custom calculator you just manufactured, that is what we call a closure. Because it closes over the lexical scope of the environment where it was born.
Closes over it.
Yeah.
Yeah.
Even after the outer factory function has finished running and completely exited, that inner function still perfectly remembers that x was -500.
Wait, how does it remember that? Because in a language like C, once a function finishes executing, all its local variables get popped off the stack and destroyed.
Well, the JVM garbage collector is actually smart enough to realize that the inner function still holds a reference to that x variable. Since you're passing the inner function back out to the main program, the runtime just preserves the environment it needs to survive.
That is wild. And there's a specific syntactical detail in the notes about how you actually save this closure right. We capture this custom calculator using the def keyword, not defin.
Yes, which is a really vital distinction. You use defin when you're writing a completely fresh function from scratch in your source code. You use def here because the function already exists. Your factory just dynamically manufactured it. And you are simply binding that existing closure to a variable name so you can use it later.
So I bind my -500 calculator to the name, say my adder, and then later on in my code, I can pass the number 20 into my adder, and it instantly spits out -480.
Exactly. You dynamically generated custom logic at runtime.
That's incredibly powerful. But eventually, any real program needs to loop. It has to iterate over lists of data. If our data structures are strictly immutable, we can't use a traditional for loop where an integer increments from 0 to 10. So how do you loop without a mutable counter?
You rely on recursion. So instead of a loop block iterating, a function processes the first item in a collection and then just calls itself, passing the rest of the collection down to the next execution.
But every CS student knows the danger of naive recursion. Every time a function calls itself, the system pushes the return address and local variables onto the call stack. If I use basic recursion to process like 100,000 database records, I'm going to blow right past my memory limits and get a Stack Overflow error.
And that is the exact limitation of standard recursion. But Clojure solves this with something called tail recursion optimization, and it uses two specific keywords to do it: loop and recur.
How does recur bypass the stack limit?
Well, when you set up a loop block, you define your initial starting values. Then you run your logic inside the block. When the execution hits the recur keyword at the very end, the compiler does something brilliant. Instead of making a new function call and pushing a new frame onto the stack, it acts like a highly optimized GOTO statement.
Oh, so it literally just jumps back up to the top of the loop block.
It jumps back to the top, but it seamlessly binds your newly calculated values to the local variables for the next pass. It overwrites the values in the current stack frame instead of creating a new one.
So you get the memory safety and the constant space execution of a while loop, but you maintain the strict immutability of functional programming.
Exactly. It's a really elegant compromise between mathematical theory and hardware reality. But honestly, as you dig deeper into the functional paradigm, the notes point out that manually writing loop and recur isn't even the preferred way to process data.
Really? It usually isn't.
No, because as you embrace functional programming, you start to move away from micromanaging the iteration entirely. You lean on higher order functions that are built right into the language, like reduce.
Oh, yeah, reduce! That looked like magic at first glance in the notes. Like, if I have a vector of 50 numbers, I don't write a recursive loop to add them up.
No, you just take an aggregator function, like the basic plus operator, and you pass it directly to reduce along with your vector.
So under the hood, reduce is taking the first two numbers, adding them together, and then holding on to that running total. Then it grabs the third number, passes the total and the third number back into the plus operator, gets a new total, and just rolls down the line until the vector is empty.
That's exactly it. It completely abstracts away the mechanics of the loop. You're no longer instructing the computer how to iterate through the memory. You're just telling it what mathematical transformation you want applied to the collection.
That really is the paradigm shift right there. You stop acting like a micromanager, telling the CPU where to move every byte, and you start acting like an architect, just defining the logical transformations.
And that is exactly the mindset you need to adopt this week. Because the concepts we've covered today, they aren't just academic theory, they are the survival skills you're going to need for your immediate coursework in CS330.
Speaking of coursework, let's talk about the schedule for a second, because looking at the syllabus, the rubber is about to meet the road. Lab 10, which dives into code generation, kicks off on Wednesday, April 15th, so you need to be prepared for that.
Yeah, but before you get deep into code generation, you've got an immediate hurdle with today's material. Lab 11 is an in-class lab specifically focused on Clojure.
Right. Lab 11 is due the following Wednesday, April 22nd. You'll literally be dropping into the REPL, wrestling with that prefix notation, and actually writing closures and recursive loops. And you really can't afford to fall behind because that massive Lab 10 compiler project comes due right on its heels.
Right. Part 1 of Lab 10 is due Monday, April 27th, and Part 2 is due Wednesday, April 29th.
So the next 2 weeks are going to require you to rapidly context switch between functional programming in Clojure and imperative compiler construction. It's definitely challenging, but understanding how languages parse code will help you in both areas.
Absolutely.
And to that end, I want to leave you with one final thought as you head into your lab work. We spent a lot of time today talking about homoeconicity, the fact that in Clojure, code is data and data is code. The compiler parses your executable instructions the exact same way it parses a static list of strings.
It's a really profound architectural truth. The language fundamentally cannot tell the difference between a data structure and a program structure.
Right, so think about the implications of that. If your code is literally just a data structure that your program can manipulate, what happens when you write a program designed to modify itself? Like, what kind of boundaries can you push when your software can actively rewrite, evolve, and expand its own logic on the fly while it's running?
It's a whole different ballgame.
It completely changes what a programming language can be. Good luck with the REPL this week. Wrap your head around those parentheses, and we'll catch you next time.